Hey there, chemistry students. Sorry, STEM chemistry students. This is Ms. Ruark. This is Vodcast 8.4, where we're going to learn about solutions and how things have, why things dissolve, and how to make solutions and different types of solutions. Okay, so a solution is formed when one substance disperses evenly throughout another. Okay, and then the solution involves the interaction, it should say involves, the interactions of intermolecular forces, which is why we're doing this right now, because we just learned about intermolecular forces, right? And a solution forms when the attractive forces between the solute, the thing being dissolved, and the solvent, what's dissolving it, are equal in magnitude to those that exist between the solute or solvent. Okay, so let's think Kool-Aid. If you were to take a Kool-Aid packet and you were to make Kool-Aid with it, the Kool-Aid packet would be your solute and the water would be your solvent. Okay, dissolving. This is the process of dissolving starts with something we call solvation. Okay, so solvation, not salvation, solvation occurs when the solute particles are completely surrounded by the solvent molecules. Okay, and if the solvent in particular is water, we call this process hydration. Okay. For a solution to form, like must dissolve like. So like dissolves like. You'll hear me say that a lot. What does that mean? That means that a nonpolar substance will dissolve a nonpolar substance. Nonpolar does not dissolve polar. Okay, so water and oil, we say oil and water don't mix. Well, why? Because oil is nonpolar and water is a polar substance. All right, so why don't they mix? Well, let's look at it. Here we have a mixture of water and oil. Okay, so what happens here is that the slightly negative ends and the slightly positive ends of this water are going to start to attract each other. That's what we call hydrogen bonding, right? Hydrogen bonds. Okay, so they're going to attract each other. And when they attract each other, they're going to move closer due to those electrostatic forces. Okay, so what do? They move closer. Well, when they move closer, they're going to push those water molecules out of the way because there's no attraction there. And since there's no attraction there, they just slip and move out of the way. Well, they keep pulling closer and closer, and when they pull closer and closer and closer together, here's your water molecules all put together. The oil, being less dense, will be pushed out of the way and it will actually float up at the top. And that's why oil and water don't mix. So the nonpolar substance is going to be pushed away. If it were moving faster, it might be able to break through those attractive forces, but it doesn't. All right, so solubility is just a balance between speed and attraction, and the more similar the strength of their dipoles, the more likely two compounds are to mix. Okay. All right, so let's talk about soap. Why are you talking about soap? Well, let's just talk about soap for a minute. All right, so here is your soap molecule. This is what it looks like, similar to this, whatever. All right, so your soap molecule has a hydrophobic nonpolar end, which is your carbon chain. Okay, the reason it's hydrophobic and nonpolar is because there are there's an equal distribution of hydrogens, and it has all to do with the arrangement and the equal pool of electrons, so it's nonpolar. Okay, but guess what? You also have this polar end. It's a hydrophilic. Okay, hydrophobic meaning water fearing, doesn't like, and then hydrophilic meaning water loving polar end. And that hydrophilic polar end is going to be polar because of these on the phosphate. Okay, that phosphate here has these oxygens, which gives it an overall -3 charge, and that's going to pull on the slightly positive ends of the water molecules. It's going to pull them in nice and close. Okay. All right, so this is what your soap molecule would look like. Well, what happens if we put a drop of grease in water? Okay, so here's our nasty little drop of grease. All right, this drop of grease has been put into water. We know that grease is non-polar. Why? Because grease is oil, right? Oil. We said it was non-polar. All right, well, water we know is a polar substance. And so the water is not going to dissolve the grease. Well, the question is, how are we going to be able to wash grease or oil away if it doesn't dissolve in water? Well, we use soap. And the reason we use soap is because soap lets you dissolve the nonpolar in the polar. All right, so how does this happen? Okay, well, here we have the grease and the soap. Okay, so the soap is a hydrophobic end and a hydrophilic end. Okay, this is the hydrophilic end because it is water loving, and this would be the hydrophobic end. The hydrophobic ends pull in together and dissolve the grease, and they make kind of like a big old circle. The hydrophilic ends dissolve in water. Okay, so what it does is it kind of just makes it makes like a micelle, and it just encapsulates this and pulls it away. Okay, and so the water molecules will surround and dissolve the grease, and then they help get the grease out of your way. Okay, this is similar to phospholipids in biology, right? Phospholipids. Okay, so phospho meaning the phosphate, so that end of it, and then lipids meaning the fats. So it's very similar to what you learned in biology with the phospholipid membrane. Okay, and just so you know, chemistry is just the driving force for everything that you've learned in biology. So it explains why biology happens. Yeah. Chemistry rules. Okay. All right, moving on. Okay, so in order for like to dissolve like, two things must be considered. Okay, and this is what we're going to consider. In order for a process to happen, energy. The energy content of the system, processes in which the energy content of the system decreases tend to occur spontaneously. Okay, so if the energy decreases, it's going to occur spontaneously. Well, then we also have this thing called disorder. Now, you guys know what disorder is. I'm sure your bedrooms have a little bit of disorder. Maybe your notebooks have some disorder. Some of you are very, very organized. I'm sure you have some disorder somewhere, but some of you are not very organized. And so you have this thing called entropy, which is disorder. And the entropy is a process in which the disorder of the system increases, and they tend to occur spontaneously. All right, so what in the world, why are we talking about this? Well, because you have to have energy to put into something in order for a solution to be made. Okay, and you can see entropy or disorder. This is favored in the world. How do we know that? Because, think about it, you have to put energy into cleaning your room, right? You have to put energy into keeping your room clean. If you don't put energy into keeping your room clean, what happens? Disorder takes over. Yeah, okay. All right, so formation of solutions is favored by the increase in entropy, which is disorder, that accompanies mixing something. So in order to get a solution to happen quickly, the best way to do that is to stir it. Right? If you stir it, you're agitating, you're disordering, you're moving things around. And also if you increase the temperature. If you increase the temperature while you're making a solution, it should make the solution quicker. Things should dissolve quicker because you're increasing that kinetic energy, which increases the disorder. Oh, it all comes together. I know. Okay, so saturated solution. There's different ways we can talk about a solution. A saturated solution is one in which no further solute can be dissolved. Okay, solubility, when we talk about solubility, we're just talking about the given amount of solute that can dissolve to give a saturated solution. So when we say that we're trying to make a saturated solution, the solubility just says how much can we dissolve at a given temperature or pressure. Okay? Well, we can also have something that is an unsaturated solution, and that's one in which we can dissolve more solute. And then, well, what if we dissolve a lot of solute and then we force it to dissolve more by increasing the temperature or vigorously stirring? Well, we call that a super saturated solution. And hopefully I will remember, or one of you guys will remind me, and I'll show you an example of this right here. I'll show you a video of it, because a supersaturated solution can look normal. It can look like it's just a regular solution, but it can be slightly disturbed or agitated, and it will crystallize immediately. It's the coolest thing ever. Okay. This right here is called a solubility curve, and this is what we would use to talk about the difference between saturation and supersaturation and unsaturation. All right, so here, this is the saturation, or the line for salt, and this would be the conditions for saturation. All right, anything below this would be considered an unsaturated, if we're just talking about salt, NaCl, and anything above it would be considered a supersaturated solution, because this solubility curve tells us that, and this is the solubility in grams of salt in 100 grams of water, that at 0 degrees Celsius we can dissolve about 34 grams of salt in 100 grams of water. If we go more than that, we've got a supersaturated solution. If we go less than that, we've got an unsaturated solution. Okay? If we had it at 100 degrees Celsius, then we could dissolve approximately 40 grams in 100 grams of water. Anything above that would be supersaturated. Anything below that would be unsaturated. Okay, we can do the same thing with all of these things. We can do it for lead 2 nitrate, potassium chloride, and this will give us, it just helps us to define how much solute we would need to make a saturated, unsaturated, or supersaturated solution at a given temperature. All right, solution equations. So we're not going to do any calculations on this podcast, but I will show you the equations and then we'll practice them in class. I'm sure you guys will have plenty of questions and we'll go through them then. All right, so different ways that we can talk about concentration. So one of these would be that we use, this is the most common, and it's called molarity. And molarity is the number of moles of solute dissolved per means divided, liters of solution. And it's a big M is the unit for it. So when we did our lab and we had 2 m HCl, 2 molar HCl, it just told us the concentration. Okay, so the unit of that would be moles of solute per liter of solution. So if it's 2 molarity, it would be 2 moles per 1 liter of solution. It's probably starting to make sense now, right? Okay, you can also have a dilution equation, and the dilution equation just tells us how to dilute or how it has been diluted. And just remember, a diluted solution contains less solute. You'll actually do dilutions in class. Yay, so much fun. The dilution equation that you'll need to have is M1V1 is equal to M2V2. M being molarity, V being volume. Okay. All right, percent mass. Percent mass for a solid and a liquid, a solid being dissolved in a liquid. Okay, so percent mass, you would have an equation that looks like this, where you have your mass of solute in grams divided by the volume of the solution in milliliters times 100 gives you your mass percent. Molality, which we'll use in the next podcast a lot. Molality is a little m, and that is the number of moles of solute divided by kilograms of solvent. So this one varies from molarity. Molarity is moles over liters of solution, and molality is moles over kilograms of solvent, so slightly different. And then we have mole fraction, which is the ratio of the number of moles of a given component to the total number of moles of solution. All right, and here we have the equations for that, and that would be X is equal to the mole fraction, and N is equal to the number of moles, A is the solute, and B is the solvent. Okay, and I think, well, this is my cute little thing that I have for this one. I'm going to run out of time. Factors affecting solubility, I talked about this a little bit. The structure, like dissolves like. Surface area, greater surface area tends to lead to greater solubility. If you increase the pressure, the solubility will increase. The temperature, for an aqueous solution, typically if you increase the temperature, you're going to increase the solubility. Right? And sometimes just an increase or decrease in the solubility of a solid with an increase in temperature. I think that's what I wanted to go there. Okay, guys, that's it, and I will see you in class.